Welcome, students, to the captivating realm of physics, where curiosity meets discovery. As we embark on this intellectual journey, I encourage you to explore the wonders of the universe, from the smallest particles to the vast cosmos. I invite you to view our latest video, which delves deeper into this fascinating subject. Kindly subscribe to our channel for ongoing insights and discussions that will ignite your passion for learning. Together, let us uncover the mysteries of nature.
Now let us study about the production and properties of electromagnetic waves. How these electromagnetic waves are produced, that is by Hertz experiment. Maxwell's prediction was experimentally confirmed by Heinrich Rudolf Hertz in 1888. The experimental setup used is as shown in the figure 5.7b. It consists of two metal electrodes which are made up of small spherical metals. These are connected to larger spheres and the ends of them are connected to induction coils with very large number of turns. And this is to produce very high electromotive force, EMF. Since the coil is maintained at very high potential, air between the electrodes gets ionized and spark is produced. The spark means discharge of electricity. This discharge of electricity affects another electrode which is of ring type and which is not completely closed, and that is kept at far distance. This implies that the energy is transmitted from electrode to the receiver, thus the ring electrode, in the form of waves, and these are known as electromagnetic waves. And if the receiver is rotated by 90 degrees, then no spark is absorbed by the receiver. This confirms that electromagnetic waves are transverse waves as predicted by Maxwell. Hertz detected radio waves and also computed the speed of radio waves, which is equal to that of light. That is given by 3 × 10⁸ meter per second. And this LC oscillator circuit with proper setup can be used to generate radio waves whose frequency is the same as that of LC oscillations, given by f is equal to 1/2 pi root of LC Hertz. Now let us see the properties of electromagnetic waves. These electromagnetic waves are produced by any accelerated charge. Electromagnetic waves do not require any medium for propagation, so electromagnetic wave is a non-mechanical wave. Electromagnetic waves are transverse in nature. The oscillating electric field vector, oscillating magnetic field vector, and propagation vector, which gives the direction of propagation, are all mutually perpendicular to each other, thus as shown in this diagram. This electromagnetic wave is transverse in nature, and here this E is the electric vector, that is electric field, and B is the magnetic field vector, that is the magnetic field which is perpendicular to each other, that is the electric vector and magnetic field vector, they are perpendicular to each other, and this direction of propagation of this is again mutually perpendicular to both electric and magnetic field vectors. Here, for example, if the electric and magnetic fields are as shown, then the direction of propagation will be along the x direction. Then the electromagnetic waves travel with the speed which is equal to that of light in vacuum or free space. So c equal to 1/root of epsilon naught mu naught, that's given by 3 × 10⁸ meter per second, where epsilon naught is the permittivity of free space or vacuum and mu naught is the permeability of free space or vacuum. And in a medium with the permittivity epsilon and permeability mu, the speed of electromagnetic wave v is less than that in free space or vacuum. V is less than c. And in a medium of refractive index n, which is given by c by v, that's given by 1/root of epsilon naught mu naught by 1/root of mu epsilon. So here n is equal to root of epsilon r mu r. This epsilon r is the relative permittivity of the medium, which is also known as the dielectric constant, and mu r is the relative permeability of the medium. Electromagnetic waves are not deflected by electric field or magnetic field. Electromagnetic waves can exhibit interference, diffraction, and polarization. Like other waves, the electromagnetic waves also carry energy, linear momentum, and angular momentum. If electromagnetic wave incident on a material surface is completely absorbed, then the energy delivered is U, and momentum imparted on the surface is P equal to U by C. If the incident electromagnetic wave of energy U is totally reflected from the surface, then the momentum delivered to the surface is given by delta B equal to U by C minus of minus U by C. That's given by 2 times U by C.
Welcome everyone. Let's explore the world of electromagnetic waves. See how? Pages 272 to 273. These pages describe how electromagnetic waves are generated and their fundamental nature. Production of M waves. Any stationary charge produces only an electric field, and a charge moving with uniform velocity produces both electric and magnetic fields that do not change with time. However, an accelerating charge produces an electromagnetic wave. Oscillating charges. When a charge oscillates, an accelerating motion, it creates a time-varying electric field, which in turn induces a time-varying magnetic field. These fields regenerate each other and propagate through space as an electromagnetic wave. Hertz's experiment. Heinrich Hertz experimentally confirmed Maxwell's theoretical prediction of M waves using a transmitter and receiver setup. Nature of M waves. These waves are transverse in nature, meaning the oscillating electric, vec E, and magnetic, vec B, field vectors are perpendicular to each other and also perpendicular to the direction of propagation of the wave. 10 multiple-choice questions, MCQs. Which of the following is required to produce an electromagnetic wave? A. A stationary charge. B. A charge moving with constant velocity. C. An accelerating or oscillating charge. D. A neutral atom at rest. In an electromagnetic wave, the angle between the electric field vector, vec E, and the magnetic field vector, vec B, is a 0 circ, b 45 circ, c 90 circ, d 180 circ. Electromagnetic waves are a. Longitudinal waves, b. Transverse waves, c. Mechanical waves, d. Stationary waves. According to Maxwell, a changing electric field produces a stationary magnetic field, b. A time-varying magnetic field, c. No field at all, d. Only gravitational force. Who experimentally confirmed the existence of electromagnetic waves? A. James Clerk Maxwell, b. Michael Faraday, c. Heinrich Hertz, d. Isaac Newton. The direction of propagation of an electromagnetic wave is given by the direction of a. Vec E, b. Vec B, c. Vec E, times Vec B, d. Vec B, times Vec E. In Hertz's experiment, the frequency of the electromagnetic wave produced is equal to a. The speed of light, b. The frequency of the oscillating charge, c. The square of the electric field, d. 0. An electromagnetic wave can travel through a. Only solids, b. Only air, c. Both vacuum and material media, d. Only through wires. The velocity of electromagnetic waves in a vacuum is approximately a. 3 times 10 to the power of 8, text, ms, caret, -1, b. 330, text, ms, caret, -1, c. 1500, text, ms, caret, -1, d. 3 times 10 caret, 10, text, ms, caret, -1. When a charge is at rest, it produces a. Both vec E and vec B fields, b. Only an electric field, c. Only a magnetic field, d. Electromagnetic waves. 10 2-mark questions. How are electromagnetic waves produced? Explain why an accelerating charge is necessary for the production of M waves. Define the transverse nature of electromagnetic waves. What is the role of a time-varying electric field in the propagation of an M wave? State the relationship between the frequency of the source and the frequency of the produced M wave. What did Hertz use as a transmitter in his famous experiment? How is the magnetic field, vec B, oriented with respect to the electric field, vec E, in an M wave? Mention the two fields that constitute an electromagnetic wave. Does a charge moving with uniform velocity produce m waves? Why? Sketch a diagram showing the relative orientations of vec E, vec B, and the direction of propagation for an m wave.